So as tension was basically action-reaction force, a normal reaction, as the name itself has a reaction word in it, it's again from action-reaction. So say there is this block, this mass on this platform. Now why is the mass not going through this body? Why is this block not going through this platform, which is the book over here? Why is it not going through? That's pretty obvious that obviously it will not go through. But then what's the exact reason? Or maybe not the exact reasons because we are not going to the microscopic level. But on the macroscopic level, what's the reason? So that was your platform. This is your mass. It is having a force of, it is being pulled down with the force of mg by earth. So my question was, why is it not going through? The obvious reason is because there was a platform below it. That platform is stopping it. So how is the platform stopping it? By giving it a force, by giving it a ulta, opposite force. So how is that opposite force acting on all the contact parts of the body? There it is having a reaction backwards. So considering all the forces as one force, we'll make a reaction force backwards, which is called the normal reaction. Why it is called the normal reaction? Because it happens to be at 90 degrees to the bodies in contact. It is perpendicular to the bodies in contact, hence the word normal. And it's a reaction force, hence the word reaction. So the body below has pushed it up. Now we know that the body is not going anywhere. We know that this black body is not going anywhere. It is at the same place. So we can extrapolate that the upward force must be equal to mg in this very case. So this is a situational fact. The body is not going up or down, hence normal reaction is equal to mg in this case. Had the body been going up, like for instance now, if the body is going up, then the normal force is not equal to mg. Then what is happening is that black body is experiencing a push from the bottom. It is experiencing a push from the bottom and it is going up. So that normal reaction, the push from the bottom, which is called the normal reaction, is overcoming the weight of the body, which is mg. And in this case, n must be greater than mg. Then only it's going up. And in the case when the body is going down, if the body is going down, then your normal reaction must be less than mg. Hence mg wins. Hence the body must be going down. So the normal reaction is not the weight of the body. You have to look at the situation and then you have to figure out how much is the normal reaction. So I'm repeating this again because after few problems and few questions, particularly when most of the questions initially your normal reaction comes equal to mg, you get into habit of writing n is equal to mg, which is all wrong, which is totally wrong. And on a wedge, we'll just discuss very soon, you get into habit of writing n is equal to mg cos theta, which is again wrong. It might be equal to mg cos theta in some situations, but it is not always this. So normal reaction is a reaction. Force from the body which is in contact, like over here. This duster is in contact with the whiteboard. So let me draw the whiteboard in red and the duster in blue. Then what is happening? Due to magnetic attraction, is actual magnets now, and the board is magnetic. The wall or the whiteboard is pulling the duster towards itself. It's pulling the duster. So the duster is pressing the wall. So why is it not going in? Because the duster has pressed the wall, then the wall is pushing. That pull was due to magnetic force. This blue thing is due to the magnets. Now since it is pressed onto the wall is pressing it back. It doesn't allow it to go through it. It is pressing it back. Had it been a water kind of wall, it would have gone in. But it is a rigid wall, it is pressing it back. So it is pushing it back, and since we can see it is neither going forward nor back, Hence, we can say this reaction force, this normal reaction force is equal to the pull force, which is F over here. So you get F equal to the normal reaction R in this case. Now, why is the duster not going down? There is a downward force from Earth, which is mg of the duster. So why is it not going down? So we very well know, due to this contact, and the contact not being frictionless, this part is having a lot of friction. The friction must be holding it up. So let me draw the friction in black. The friction must be holding it up, and we can extrapolate that this friction must be equal to mg, because the duster is neither going up nor down. Had it been going down, like I leave it this side, there's still some magnetism, it is going down. Why? Because the friction is too less to hold it. And the friction will come into play when there will be a push on of one object on the other object. When one object will be pressing onto the other object, then only the friction will come into play. But anyhow, I'll discuss friction much later. So we are discussing normal reaction over here. So again, I'll emphasize the fact I'm standing on the ground, and why am I not going down? Why I'm not going under the floor? This is me standing on the ground, and why am I not going under the floor? Because why I should go? Because Earth is pulling me down with mg force. Why am I not going? Because the ground is pushing me back up with normal reaction, maybe N1, N2, depending on how much of press I'm giving to the floor on by both my legs. If it is equal, both will be equal. But no doubt that N1 plus N2 must be equal to mg if I am standing without my center of mass going up or down. I can manage to jump up also, by the way, using the normal reaction. I can accelerate upwards using the normal reaction. So that is when your normal reaction has exceeded mg. And how I manage that, we'll again discuss a bit later. But I hope you got a understanding of what normal reaction is. So this part normal, I'm just going to emphasize a bit more. The bodies, whenever we draw these flat bodies, it is easy to get those, but I'll draw different kinds of bodies. I'll draw flat body also. So one in red and one in black. Say the first one, what we drew, one body onto the other body. The black body will push the red body. So black body pushes the red body and up. This push force acts on the red body, and the red body pushes the black body down with the equal and opposite N force. This N is equal to that N. The black N is equal to the red N. They are equal and opposite. That's your third law of motion. Here nowhere I'm having mg anywhere. I could have drawn them one beside the other to avoid a confusion with mg. Normal reaction is not mg. Normal reaction is not mg. If these two bodies are forced on each other, if these two bodies are pressed on each other, what will happen? The red body is going to push the black body, and the black body is going to push the red body with equal and opposite forces N and N. N will be equal to N. So that's your normal action reaction, and it happens at 90 degrees to the surface in contact, to the surfaces in contact. So another case would be, if I have a sphere which is getting pushed on, or a disc maybe which is getting pushed on to another sphere or disc, that's the center. So this is the point of contact. So wherever the point of contact will be, you'll have action reaction force. So the black body is going to push the red body, and the red body is going to push the black body, and this force, where will it pass from? Here, here. Put a quick comment over here. It is going to pass through the center of the other body. Why? Because the normal to the tangent at the point of contact. If I draw a tangent at the point of contact, the normal is going to pass through both the centers. So your normal force of the black body pushing the red body will again pass through the center of the the smaller sphere of the red body. So what we get over here is that your normal reaction is 90 degree to the tangent at the point of contact, and the tangent 90 degrees is radius is always 90 degree to the tangent, so it passes through the center of the two spheres. Similarly, if I had one thing flat and the other body was round like a sphere, again the normal force is going to pass from the center of that and equal opposite normal force on the other body. So two normal forces are on two different bodies. I hope that is clear. And the last example would be, you have a flat surface, you have a flat body, and the other body is a pointed body. This point has got, it is very difficult to find a normal over there. But this body is pushing the black body, so how will be the normal force? So we know that it is going to be normal to both the surfaces. So one surface is flat, then the point of contact of the other one on a very microscopic level also will become flat over there. So the normal reaction, the normal is normal to one surface contour we know, so the other surface, so the normal force on the other surface also will come to know. It will be equal and opposite. It will be vertically opposite to each other on two different bodies. So that is normal to the surface. So here also we could figure out. So if two are pointed bodies, then obviously depending on how the question is asked and how the situation is, where it slips on, how it goes, we will be able to find out the normal force. By drawing we won't be able to find. These all by diagram, no matter the body was going up, down or whatever, even if this thing is slipping on this body is slipping on this like this, the normal force will be as shown. It is irrespective of how the motion is happening. Here also, if they are pressing on, how the motion is happening is not the question. Whether this body was ultimately going to go that way or whichever way, the normal force is going to be this way. Here also, maybe this body was rolling on a surface. The normal force, action and reaction will be the way it is shown. So that's your normal action and reaction. They are equal and opposite, acting on two different bodies. It is not acting on the same body. Your mg and n, by the way, was acting on the same body. Mg was the pull from the earth. N was the force from the body below onto this. This N and mg was acting on the same body. Mg was not the normal reaction. The normal reaction happens to be on the other body, down there. So that's the confusion when we don't draw the free body diagram, when we draw into one. Sometimes you think this mg was this normal reaction, which is absolutely wrong. So I'm not going to discuss this. It is in fact going to just put in wrong things in your head. So why to get those wrong things in your head? These are the correct facts. So register those in your head and let us move on to do some problems now. In fact, we'll quickly discuss the laws of motion. So what's the first law? The first law says, if you have no external force on a body, then if the body was moving with any velocity in one direction, it will continue to move in the same direction with the same velocity. There will be no change in velocity. If there is no external force, no change in velocity. If the velocity was 0, it will remain 0. If the velocity was say 2 meters per second, it will remain 2 meters per second. If it was going in a certain direction, it will remain going in the same direction. It's not like with 2 meters per second it can change direction. Change of direction will happen due to a force. Increase in velocity will happen due to a force. Decrease in velocity will happen due to a force. So if there is no force, there is no change in velocity. It remains in uniform motion. And if there is force, that's the second law. If there is force, then there is a change in velocity. So what's the difference between the first law and second law? The second law tells you the mathematical relation that it says that there is a change in momentum and the cause is the force and they are directly proportional. So change in momentum per unit time, rate of change of momentum has been defined as the force with the constant of proportionality taken as 1 by Newton, and On solving this for a body which is not changing in mass, what we get is m dv by dt, which is F is equal to ma. So that's the famous equation. That's your second law. F is equal to ma. Father of physics gave us the mother of all equations, ma. That is F is equal to ma. A very simple equation, a very small equation, but the implications, the applications and the effects are what we are going to do. And let's see how simple you find them to be. You will find them to be very simple. I'm not trying to scare you. If you understand what it means fully, if you understand that it tells you that the net acceleration of a body will be dependent on the total unresolved forces or the total external force on the body, and the acceleration will be in direction of that force. So we'll come to that. And the third law is every action has an equal and opposite reaction. If you push something with a certain force, it is going to push you back with the same force. So mathematically quite difficult to prove, but experimentally it's easily seen. So all these laws you have been doing it from a very early age. You already know it from earlier classes. So we'll straight away go on to the problems and discuss a bit more on this, a little bit more on this, and then we'll go on to the problems.